Alright, in this video I'm going to be talking about geometric sequences and series. They're going to be pretty similar to arithmetic sequences and series, except the common pattern is going to be multiplication or division rather than addition or subtraction. So a geometric sequence is a sequence that has terms with a constant ratio, where we get to the next term by taking the previous term and multiplying it by a number. Or dividing it by a number, but we know that dividing it by a number is really just like multiplying by its reciprocal, so we'll kind of look at that. Here we've got two examples of geometric sequences. Okay. On the first one, notice that I go from 3 to 6 by multiplying by 2, and I go from 6 to 12 by multiplying by 2, and 12 to 24 by multiplying by 2. Okay, that is what makes it a geometric sequence. And we say that its ratio, call that R, is equal to 2. All right, and then the second one, I go from 9 to 3 by dividing by 3. From 3 to 1 by dividing by 3. 1 to 1/3 by dividing by 3. So that means that R is not going to be 3, but 1/3, because R is the number we multiply by each time. And it's just easier to think about geometric sequences and geometric series as having terms that are always multiplied by the same number over and over again, rather than saying, okay, some of them are getting multiplied, some of them are getting divided. Now, I'm going to give you the formula for the nth term of a geometric sequence, but you're going to see that it's very similar to the formula for the nth term of an arithmetic sequence. Okay, it's got a lot of parallels. Okay, the two most important aspects of the geometric sequence are the first term and the ratio. If we know the first term and the ratio, we can figure out the rest of the terms, we can figure out the sum, we can do all sorts of stuff. And in general, the nth term is going to equal the first term multiplied by R some number of times. Well, however many times it takes to get from 1 to n, which is going to be n minus 1 times. Okay, you could also think about it as, okay, when I plug in 1, I need to just get a 1. I need to not multiply by R, and that would be R to the 0 power. Just be multiplied by 1. Okay, I changed it. I moved it from a center dot to parentheses, just to avoid any sort of confusion about, what number does the exponent go with? Does it go with the A1 and the R, or just the R? It just goes with the R. Because each time we're multiplying just by that ratio, not by the first term. The first term could be completely separate. And now bringing that example back from earlier, okay, I know that the nth term of this sequence is going to be the first term times the common ratio to the n minus 1. You can check that with, maybe plug in 2. The second term is 3, and is 3 equal to 9 times 1/3 to the first power? It is. Okay, so it works. And then in general, this is the formula you need to know. I forgot to highlight that. First example we've got for you is write an explicit formula for the nth term of the geometric sequence and find the 15th term. Okay, so I've got a first term here. I can see the first term is 2. And then the common ratio is 3. So if I have to write down the nth term, that's the first term times R to the n minus 1. Okay, so for this will be 2 times 3 to the n minus 1. Then the 15th term, I'm just going to plug in 15 for n. And that's just a massive number, so I'm going to bring in the calculator. And I will just type it in just like I see it. 2 times 3 to the 14. And get some massive number. 956 5938. All right. All right. This next example, just the same. I'm going to kind of get you most of the way there, but I would like you to try to take it the rest of the way on your own. But let's try to identify the common ratio on this one first. I think this one's a little different. Okay, so you think, what do I multiply 2 by to get 4/3? Maybe it's not entirely obvious. And when you've got the fractions, though, and you know it's a geometric sequence, one thing you can do is you can kind of just look at the fractions and look at the top and the bottom separately. So you got 4/3, you've got 8/9, and you've got 16/27. You see that on top, I'm multiplying by 2. And on the bottom 3, yes, exactly. You see what I'm doing. So what would you think that makes the ratio? 2/3, yes. That's all you do. That means that the ratio is 2 on top and 3 on bottom. So that means we've got the ratio. We've got the first term here. Okay, so why don't you see if you can write me an explicit formula for the nth term of the geometric sequence and see if you can find me the 15th term. If you're watching at home, you should pause the video because the answers are going to pop up here in a second. All right, there you go. So, once you've identified your first term and your common ratio, it's just an issue of plugging into the general formula. Okay, so you get the nth term is 2 times 2/3 to the n minus 1 power. If you want the 15th term, you plug in 15 for n, because that's really what n means, it's the nth term, so the 15th term is n equals 15. And you get 2 times 2/3 to the 14th power. Now, 2/3 to the 14th power, that's a really tough fraction. Calculator can't really deal with that and give you an exact value, so it gives you a decimal number. But I'm going to show you how you would get an exact answer if you just absolutely had to. Like if you had to match it up with, say, a bunch of choices on a multiple choice test or something. So I'm going to bring in the calculator. And I'm going to find, okay, say 2 to the 14. I'm going to do these separately. But then I also know that I'm going to be multiplying by 2/1 at the end. So I'm going to multiply in another 2. And that could be the numerator of my fraction, 32,768. And the denominator of the fraction is going to be 3 to the 14. Okay, so then I do 3 to the 14, and I get, some really large number, and that's going to be the denominator of the fraction. Right, so you kind of just draw a little fraction bar in there, and that would be an exact answer. That's how you could use the calculator to get an exact answer if you needed to do that. All right. Now we're going to add the terms of a geometric sequence together and call it a geometric series. Just like we did with the arithmetic sequence, we added the terms together. We call that an arithmetic series. We're going to use that same large sigma operator, okay, to indicate that we're going to make some sort of sum of these terms. Now we see that, here our sum ands are geometric because each time we increase n by 1, we are multiplying by another power of r. And see, this is a finite geometric series because of the sum ending at k. We have a formula for the finite sum of a geometric series. Okay? It's this first term a times 1 minus r to the k over 1 minus r. And I can show you why this is true, and I'll include the proofs of this equation and the infinite geometric series equation at the end of this video. Okay. And so let's just start with an example. Okay, so we're going to add from 1 to 35, 5 times 1/2 to the n. Okay, so this is a series that starts with n equals 1, so it's 5 times 1/2 to the first power, plus, and then each time we're multiplying by 1/2 because this is the common ratio. Okay, so I've got 5/2 plus 5/4 plus 5/8 all the way up to 5 over 2 to the 35th power. Okay. Now we've got a formula for this. Okay, we're going to use the formula up here in red. So a is the first term, that's 5/2. And then 1 minus the ratio to the kth power. The ratio is 1/2. K is 35. Divided by 1 minus 1/2. Okay. Now I'm going to show you what happens if you type this into the calculator. All right, so I've got the calculator here. I've got it typed in just the same way. And I'm going to press enter, and it's going to just say it's 5. Okay, and that's because it is so close to 5 that the calculator has lost track of the difference between the value of the number I've written in blue and 5. It's exceeded the tolerance of the calculator, basically. And so we say this is 5. But we know that this is not actually equal to 5. It's just really close. Okay, but so close that the calculator can't tell the difference. Now the thing is, if you look at this formula, and you think of what happens as k gets really large, okay, and r is, a fraction. This is definitely predicated on r being less than 1, at least in absolute value. But you keep multiplying over and over again by a number that is less than 1, it's going to get smaller and smaller and smaller. Okay? So as k gets larger, it's basically becoming a 1 in the numerator. Okay? And there we'll have more on this in a second when we go to the infinite geometric series formula. Right? Now the infinite geometric series is where we just keep adding terms forever, where this goes to infinity, right? And you might be thinking, how are you going to add together an infinite number of, say, positive numbers and get anything that's not positive infinity? And I'll show you here in a second. I've got an example of something that I think you should be able to think through and say, okay, I can see how this could potentially happen. Okay, I just gave you the formula now. And again, if you're interested in where this formula comes from, keep watching until the end of the video because I'm going to show you. All right, so it's equal to the first term, which is a, times 1 over 1 minus r. And, I write this, especially since it's something we need to know, we're going to say S infinity is equal to first term because we don't always know that n begins at 1. It's the first term of the series multiplied by 1 over 1 minus r. This is only valid when r is less than 1 in absolute value. So r is between -1 and 1. So if the common ratio of a geometric sequence is between -1 and 1, and we go to add up the terms of the sequence infinitely, we can say that the series converges. Okay? Which means that, the more terms we add on, the closer and closer we're getting to this one particular value. So I want you to think about, maybe it was your birthday recently. And if it wasn't, you can think back to when you last had a birthday. And you had a cake. Maybe on the day of, you either, ate some with your family or you had some friends over for a party, something like that, and half of the cake got eaten. So you started off by eating half of the cake. And then after that, the day after that, it was really good, and so you just ate half of what was left. So you actually ended up eating a fourth of the cake on the second day. That's probably too much cake, but, just for the sake of the mental exercise. Then on the day after that, you want to keep the celebration going, so you're only going to eat half of what's left. Just keep eating half of what's left. And then we're going to keep doing this. Okay, I'm going to just keep going to the next color on my palette. Looks like it's going to be 1/16. Okay, then 1/32. And then, a 64th and a 128th, and so on. Okay, for the sake of the adding up an infinite number of numbers. So we're not actually talking about cake here, 554. But yes, I see your point. At a certain point, it's going to become like, okay, it's so small, it's not even worth eating. Yes, I get your point. Just think about adding a half to a fourth to an eighth to a 16th. The more I eat, how many cakes total have I eaten? Closer and closer to how many cakes? 1 total k. Okay? So if I keep adding a half to a fourth to an eighth to a 16th to a 32nd and so on, that sum is going to approach 1. And let's try to reconcile that with the formula. Okay, this is a geometric series with first term 1/2 and common ratio 1/2. Okay, so we know that the sum is equal to this. Okay, 1 minus a half is a half, so 1/2 times 1 over a half is equal to 1 total k. That's what we're saying. Okay, so when you say that the series converges, are we ever actually eating all of it? Are we ever, equaling the number? Probably not. But we are getting closer and closer. We're converging onto that number. Okay, and this is a calculus concept. It's a thing that we do in Cal BC. Okay. But it fits really well into college algebra as well. All right, back to what I was talking about earlier. And let's go back and let's pull that same series that we were looking at earlier with the 5 and the 35 and stuff. I'm going to pull that real quick. All right, there we go. And so we started with 35, but we actually exceeded the tolerance of the calculator by using 35 terms. So I'm going to actually replace this with infinity, and I'm going to show that this series converges to 5. And it converges probably quicker than you would think. Okay. So what I'm doing is I'm going to use the infinite geometric series formula. The first term is where n equals 1. That's what we're saying right there, starting at n equals 1. So I'm going to plug in n equals 1. I'm going to get 5/2 as the first term. 1 over 1 minus the ratio. Well, the ratio in this case is the number that we're taking to the nth power, the n minus first power, something like that. That's the half. And that's 5/2 multiplied by 1 over a half. Again, the 2 and the half are going to cancel, and it's just 5. Okay. So that's what the series is converging to. Now, the sum of the infinite geometric series is going to be much more important to us in this class than the sum of the partial geometric series. Okay, there's going to be more questions about that. Now, the last thing I'm going to do is I'm going to prove these formulas for you. Okay, so I'm over here, and I'm saying that the sum from n equals 1 up to k, the partial geometric series, is equal to that first term times 1 minus r to the k over 1 minus r. Okay. And what I'm going to do is I'm going to actually write out the terms of the series. I'm going to say S equals A plus A times R plus A times R squared all the way up to A times R to the k minus 1. Okay. And then I'm going to multiply both sides of this equation by r. So it's AR plus AR squared plus AR to the third all the way up to AR to the k minus 1. And then when I multiply this last term here by another r, I'll actually have A times R to the k. And I'm going to label these as equation 1 and equation 2. And then I'm going to consider equation 1 minus equation 2. And I'll have S minus R times S, that wasn't very good, equal to. And then when I go to subtract, I'll have, right here, I'll have AR minus AR is 0, and AR squared minus AR squared also 0. All of these things are going to subtract to 0, okay, except for the A and the A times R to the K. So now I'm going to do a little factoring. I'm going to factor the S out of the left side, and I'm going to factor the A out of the right side. And then what I'm going to do is I'm going to divide both sides by 1 minus R, and I'm going to get A times 1 plus R to the K over 1 minus R. Okay, and I'm realizing I had claimed that it was 1 minus R to the K. Yeah. Hold on just a second. Oh, I see it. I made an algebra error when I basically had when I subtracted equation one or equation two from equation one, I had 0 minus a times r to the k, which would be negative a r to the k. So this would become a negative sign here. Then these two would also become minus r to the k. So I didn't think I had the wrong formula. So it's not it. But this partial sum is not really something that we do in calculus, so I, run into it less often. Okay, that's the proof of the formula for a partial geometric series. So I've got the sum from 1 to infinity of a times r to the k, right? We're going to let this sum go all the way to infinity this time. And, okay, this is... well, oh yeah, we already have the formula for this. I've told you all this. This is the first term, which is going to be a times 1 over 1 minus r. And the proof is going to be almost identical. So the infinite sum is going to equal a plus a times r plus a times r squared, and so on. And then I'm going to multiply both sides by r again, just like I did before. I'll have AR plus AR squared, AR to the third, all the rest of the powers of A. Okay, I label these as equations 1 and 2. And just like at the beginning of this course when we were doing substitution and elimination, I'm going to eliminate by subtracting equation 1 minus equation 2. Okay, so and I'm going to have now S infinity minus r times s infinity equals a plus, well, again, ar minus ar is 0, ar squared minus ar squared is 0. All the rest will have their friend all the way up to infinity. And so I have just a plus a bunch of zeros. Right? And then what I'm going to do is I'm going to factor out the s infinity, because that's what I'm trying to solve for. And then I'm going to divide both sides by 1 minus r, which is really the same as multiplying by 1 over 1 minus r. So I've got a, and I've got 1 over 1 minus r. Now the thing is that a is the first term. So that's where I usually write in first term here. Just in case our index isn't, starting at 1 or starting at 0 if that's what you're used to in your class or whatever. Okay, so that's all I've got for you for today on geometric sequences in series. And if you need more help, you just come see me in the morning.